Good morning, everyone, and welcome to this month's FlowJo webinar, where we're going to be talking about the high-dimensional FlowJo workflow in version 10. My name is Ioannis. I'm a European application scientist at FlowJo NPT. So co-hosting this webinar is Serena Di Sicilia. She's also from FlowJo as a European application scientist. And as she already mentioned, she will be addressing your questions in the Q&A box. So make sure to type your questions, and both Serena and me we're going to support you with any question that come up. In case you have other questions, here you can find my email address, and you will find at the end of the webinar both email addresses at the end of the last slide. I will just turn off my camera because of my connection this morning. For today, during this webinar, I'm going to show you an overview of the high dimensional workflow, and specifically going from quality control, and dimensionality reduction into clustering and more advanced functions such as exploring the data further. And all of this, we're going to be both, I'm going to first present you the background and different options of those functions and how we can perform those with FlowJo. And then we're going to go into a live demo and show you how it all works up in a data set. Yes. So let's get started here. Although we're not going to be talking about how we reached many dimensions, and we're at the point that we're talking about high dimensional data analysis that I'm sure you'll hear a lot in flow cytometry. I'm not going to show you how we reach those dimensions, but I'm going to show you how this increasing number of dimensions can be translated into FlowJo, and why do we need a specific workflow to analyze such data in FlowJo. So going from low parameter experiments, so imagine we have few fluorophores to address few antigens in our cells. So this data analysis can be an easy task, right? So with traditional gating and basic FlowJo functions, we can compare different population, we can overlay those, and as you can see here in N by N view, you can overlay those and have an easy data interpretation and see which population corresponds to what. So of course, as parameters increase with a purpose to identify deeper cell subtypes, different phenotypes, and a more rare population, etc., that interpretation can become now quite challenging with traditional gating. Yeah, so now you can see in a multicolor experiment, such as here, we have in an N by N plots, you can see we have so many plots now, and we can see all the different combinations and all the different markers that we can identify for the different cell populations. So now it becomes quite difficult to analyze those, since we have an increasing number of dimensions. And so what we're going to address today is how to go from those high parameter flow experiments that you can see here in the middle, and go into a more simplistic idea of this data set into a single plot. So this plot can be an embedded space of Disney, UMAP, and other dimensionality reduction methods. So here today, we're going to generate different embeddings of data sets. We're going to perform clustering. So you might have heard already FlowSum, EXIT, or Phenograph as clustering algorithms. And we're going to use additional visualization tools such as Cluster Explorer that you can see here in order to identify what its clusters corresponds to and what is the signature expression of each one of those. So Of course, there's no dogmatic workflow. So of course you can adapt it according to your needs and to have your own workflow. For example, if you do not need any quality control, if you have very clean samples, then it's great to go ahead and perform no quality control there, right? But here I propose a workflow that we use very often that in most of the cases and most of the data set can be applied. So we begin by quality control. Then we go into concatenation or merging our samples together. Then we will perform dimensionality reduction, such as Disney, UMAP, and TreeMap. And then after dimensionality reduction, we have clustering. And finally, we can use additional tools in FlowJo to explore our data heterogeneity. Yeah. So all those functions, of course, you can perform in FlowJo v10 with either the use of plugins. So some of those functions are specific to plugins. Some are already built in, for example, merge sample together. Also, Disney as a dimensionality reduction is already built in FlowJo, but some others are only available as plugins into FlowJo. So let us start with a bit of a background for each one of those categories. Yeah, so we said we begin by quality control. So we do actually have plugins for quality control and to perform automated cleaning of our samples. So one example, and one of the most famous is FlowAI. Yeah, so FlowAI detects, it performs 3 statistical tests. It detects changes in the flow rate, instability of signal acquisition, and also outliers of the dynamic range. Yeah, so it's, as you can guess already, it's a very sensitive tool. So it can be that sometimes FlowAI can have excessive removal of events, but you can, as we're gonna see later, also tune this in order to avoid such an excess removal of events. So all quality control plugins, they give the same output. So they generate populations under your sample. So here we can see a sample, and under after running FlowAI, we will have a FlowAI good events and a FlowAI bad events population. Yeah. So if you can either manually overlay those to see where the events were removed from. So here we can see in orange color removal of data towards the end of the acquisition. And FlowAI has also the advantage of a visualization tool. So you can drag and drop this FlowAI node in the layout editor, or check the output folder after running FlowAI, and you will have this visualization to see exactly what happened with your flow rate and why exactly your events were removed from that specific region. On the other hand, you can also use Flowclean. So this is the second most frequent plugin for automated sample cleaning. So, both Flowclean and FlowAI are tools that will remove cells affected by clogs or air bubbles, and both will generate those 2 populations that we said, good events and bad events. So you can also tune those algorithms to be more or less aggressive as well. So here, let's see a comparison between FlowAI and Flowclean. Yeah, so you see our raw data here on the left. So we can see that the flow rate here towards the end is somehow decreased. And finally, we have a peak here of a lot of events passing by. So there is an instability of a flow rate here. So we can see how Flowclean and FlowAI remove those data, those unstable data. So Flowclean seems to do a better job here. So it addressed only the unstable region towards the end. But FlowAI, as you can see, it removed also excess amount of events even before the change point of the flow rate at this point. So, of course, it always depends on your, there is no competition which algorithm is the best. It all has to do with our samples, the amount and types of errors that we have, and of course, the percent of removal that we can afford. So if we study a rare population, we obviously cannot afford an excess removal that can happen with Flow AI. For upcoming quality control plugins, there's going to be a Peacock webinar. I believe that is next month. So you can go ahead and be updated in any plugins that can help you with your cleaning up the data. So then, after we cleaned up all of our samples, we want to merge all of our data in one FCS files. So in order, and this we do due to the nature of how those algorithms work in dimensionality reduction. So we want to merge all the files prior to dimensionality reduction. So basically what we're gonna do here is take a subset from its donor or treatment or whatever your experimental setup is. Gonna take a subset and therefore normalize the number of events per donor, and then we're gonna merge all of those into one FCS sample. And then we can distinguish the different samples based on the sample ID keyword. That is a parameter that is generated where its sample ID corresponds to the different donors that we merge together. So that's quite an easy step. There's no plugin required to perform this in FlowJo. And then after we have a single FCS file, so all those steps from here below, dimensionality reduction, clustering, and exploring data are all being performed into the single FCS file that we have. So now, once we've gotten our concatenated and cleaned up data, it's time for dimensionality reduction. Yeah? So now our concatenated samples at this moment are high dimensional data, as you can see on the left, with containing all the different phenotypes, all different treatments, donors, and everything all in one FCS file. So, and the reason why we use dimensionality reduction is to be in a point that we can easily visualize all those multiple parameter data into a single two-dimensional plot. Yeah. So in general, whichever dimensionality reduction method we use, whether it's Disney, UMAP, TreeMap, or PACMA, in general, each island on those embedded spaces would represent a distinct cell phenotype. Yeah, so as you can see here, my backgated population that were overlaid, we can see how they look into the different dimensionality reduction outputs. So we have a much easier representation of our CD4s, for example, in TreeMap, PACMap, UMAP, and Disney, rather by working with traditional gating and high dimensional data, where that would be impossible to explore all the different phenotypes. Sorry, it seems some my slides are okay. There we are. So there are different algorithms for dimensionality reduction. So each tool has a different way of displaying the data. So in general, UMAP and TreeMap and recently released PACMAP tend to preserve more the global structure of the data. So cells highly related to one another tend to be embedded close in the two-dimensional space rather than in Disney. So as an example here, we can take the B cells and the CD4 T cells. Yeah. So those look far away from each other in both UMAP, TRIMAP, but also in PACMAP because they have no similarities in expression. But on the other hand, you can see in Disney, they look closer to each other. So that's why we say that UMAP and TRIMAP are better into preserving the relationships between the different cell types rather in Disney. And that ultimately would mean for Disney that the white space between the clusters is important, but where they are exactly to one another, so the distances between the clusters do not matter at all. So this makes the different dimensionality reduction algorithms useful for different experiments. For example, although I talked about Disney that the distances don't matter, but Disney can be a really good option for dimensionality reduction of having knockout and wild type mice that we want very high resolution of rare clusters. Disney might be the way to go. On the other hand, if we want to preserve this global structure and see, for example, more like trajectories of one cell line going to another, or differentiation, etc., UMAP, TRIMAP, and PACMAP might be doing a better job there rather in Disney. And this we're going to see later during the demo, focusing on monocytes and differentiation of monocytes. So again, it's all about the data set of and how to choose one dimensionality reduction method over the other. Okay. So now, after we finish our dimensionality reduction, we're not done yet, because imagine now we have a two-dimensional plot that you can see here on the left, which is Disney, but we still don't have information about what each one of those clusters corresponds to, right? And we certainly don't want to draw again gates on each one of those clusters in order to explore what is their signature expression, because that would again not be a high-dimensional workflow. We would lose all the advantages of this workflow. So we want to actually use clustering algorithms in order to partition those data in different populations automatically. Yeah. So so instead of drawing traditional gates to each one of those different clusters and exploring what they mean, we can do this automatically with algorithms such as FlowJo, Phenograph, and EXIF. So this will basically generate new population under our concatenated samples. So you can see here, for example, after FlowJo, we have here 8 different clusters. Yeah. And you can use those clusters either to overlay it on your Disney, and or as we're going to see later, we can also use Cluster Explorer in order to much easier visualize the data heterogeneity. So in terms of the different clustering algorithms that we can use, here I mentioned the 3 of the most famous at the moment. So there is FlowJo, which offers this powerful visualization. Yeah, so we can have this minimal spanning tree here, where each color here corresponds to the different meta cluster. And you can see in those nodes within inside, you can see the expression of the corresponding markers that we selected. And of course, you can have this as a heat map where we have the different clusters and the MFI of each one of the parameters that we selected. It's quite fast, and the only sort of disadvantage is that we have to manually input the number of clusters. So this can make it a bit more difficult to, in case we have a new data set and we're not sure about the clusters we have, FlowJo will need you to type in the number of meta clusters that you want to have. So on the other hand, Finograph and Exif, they do not offer any visualization. But of course, you can either overlay the populations that you get out of Finograph or Exif into your dimensionality reduction method, or as we're going to see later, you can also use Cluster Explorer, which is much easier to combine the outputs of Finograph and Exif into your dimensionality reduced space. And of course, you don't have any, you don't need to input any number of clusters that you want to have, so they will both automatically detect the number of clusters in the sample. Yeah. Exif can be quite faster than Finograph, and that's because of the downsampling that it performs. So if you want a quick clustering, I think Exif and FlowJo can be the way to go for a quick clustering of your data set. And so now that we have both our clusters and our dimensionally reduced space, we need a way to identify those phenotypes of our clusters efficiently. Yeah? So that's why we have a tool that is called Cluster Explorer. And it presents to you a series of interactive panels. Yeah? So first of all, you will see your dimensionality reduction method that you choose here. It's all interactive, so you can click on any of those clusters and simultaneously see the signature expressions or the MFI of the relative expression of each one of your clusters. You can also draw gates here on your desired population, and you can also see the frequency of each cluster, which cluster is the most abundant, and of course have it all also as a heat map here. Yeah. So it's you can really dive into your data set after having a dimensionality reduction method and a clustering. Using Cluster Explorer will combine all those and make a very powerful visualization. So we can also use Cluster Explorer very efficiently in order to compare cluster enrichment across time points or different donors or specific treatments. Yeah. So here we see an example that we're also going to see later during the demo. Basically, we can use our clustering and dimensionality reduction in order to visualize, for example, going from the uninfected day 7 post-infection and day 28 post-infection, you see that we have the presence of this cluster. Yeah. So you can either do this manually in the layout editor, and you could, in theory, draw a gate here and go from time point to time point and check the frequency of those clusters. Or you have an advantage with Cluster Explorer, where you can input on your heat map your different time points or your different treatments, etc. Yeah. So ultimately now we can have a heat map where we can compare each one of the clusters and see its abundance across time points. So now we would know we can add any kind of information, whether it's as a keyword here on the columns, and we can visualize it as a heat map. So now we can see, for example, that clusters 27 to 32, for example, are enriched in the time point 3. Yeah, so it means that those during day 28 post-infection, those appeared as new clusters compared to the different 2 time points. So this way we can identify unique clusters per different time point. Okay, so that was it for the high dimensional workflow here. So I will jump now into FlowJo, and we can discover how we can all make it into FlowJo. So unless there is an open question, I see Serena has already answered. Thank you, Serena. And we can go into the FlowJo thing. Okay. Good. So I will open FlowJo here. And I would like to explain you a bit the dataset here. So first of all, I would like to thank Jack Panopoulos and for sharing with us this dataset. So basically in this dataset, we have different macaques, which are annotated as A1, A2, 3, 4. And we have different time points post-infection. Yeah? So we have the uninfected, so day 0 here. You can see I have it in a new group here, and I have 4 macaques per time point. Yeah? So we have day 0, day 7 post-infection, and also day 28 post-infection. Okay? And additionally, I have here a new group, which is called high dimensional workflow, where I have all of my different samples, so all of my different time points and macaques. So in total, we have 12 samples here. I tell you all this because I just want to focus on the fact that, you know, annotation and tidying your data and having different groups and different keywords can be a really powerful tool, and it will really make your life easier during this kind of analysis. And speaking of keywords, I have set here, as you can see, different keywords. So we have a keyword for the macaque ID. So we have 4 macaques, and I labeled those 100, 200, 300, 400, and those for the different time points as well. And also another keyword that will also help us is the day post-infection. So we have here 0 for the pre-infection, day 7, and day 28. Okay, so once we have all these, and once we annotate it and we you know, organize our data, we can proceed with a high dimensional workflow. So getting started now, the first step is quality control, as we said. Okay, so how can you realize in FlowJo that the quality of your sample is bad? You can, if you already know, you can double click here on this circle. You can double click that and see and have a quality check. Yeah. And you can see here, after pressing OK, that the quality of this sample is actually irregular. Yeah, so purple color means that we have something that needs attention from us in order to clean those bad events. And indeed, if I double click this sample here, and I put on my x-axis time, you will see that, you know, we have some interruption here of our flow rate, and indeed, possibly we need quality control for this sample. after running Flow AI, I observed on this first sample that almost half of the events were removed by all checks from Flow AI. So I decided on this dataset to go with Flowclean because it did a much better removal, so a much sensitive removal. So we can check here with Flow AI, with Flowclean. So with Flowclean here, again, the same principle. We would use all of our uncompensated parameters. Yeah. And I would, I'll just quit this one here. And then simply press OK. So after we have Flowclean done into the sample, so here we see only 5% was removed. You could actually use the layout editor to overlay those if you want. Yeah, so you can go here and overlay the good and bad events and see that indeed only in the end of our the acquisition, this part was removed. Okay, so all the rest was kept with Flowclean. Yeah, so that's a way to also visualize the what exactly Flowclean has done at this point. And then we want to do this, like we want to perform this algorithm in all of our samples. Yeah, so I can select this node, yeah, and then I can drag and drop it into my group. Yeah, and this will start calculating all of the different samples, the good and the bad events. Yeah. So I did this beforehand and cleaned all of the samples in here. So it took around, I think, 20 minutes to do all of the samples. So it's a bit slower to use Flowclean, but it really did a good job into not excluding too many of our events. So now that we have our Flowclean good events, we can use, as I said before, some sort of gating, going from the good events to CD45 and then till HLA-DR positive. Yeah. So I will use those gates now, and I will copy those. Sorry, I will copy this analysis to the group. Okay, so now you can see that I have the same analysis going from clean good events from each sample into my gating strategy. Yes. You can also delete the Flowclean node in order to avoid in any case that it tries to recalculate. And you can also, if you want, delete the bad events. Yeah, they're not quite useful anymore now. Yeah. So now going into merging of the DR positive cells, we will select our DR positive, press right click, selecting the equivalent nodes so that we have all of our DR positive cells here. And then we're gonna go into file and export concatenate populations. Yeah. So I will switch into my concatenation tab here, and then I will I can include either all events, so this will take all the DR positive cells from each sample, or I can include no more than. So, and this is a good trick in order to normalize the number of DR positive cells per sample. Yeah, so we want to have, as we said, a subset that it's identical for each one of the samples. Yeah, so we can normalize the number of events that we want here. And additionally, we have some advanced options here. You can change the name of the merge file that we're gonna do, and also you can change the way which files you want to merge together. We want to merge all the files in that case, and you can choose also additional parameters. Yeah, so I can select now my keywords in order to be transferred into my new file. Yeah, so my keywords here were the macaque ID and also the day post-infection. Yeah, and I can press OK here, and those keywords now can be used as parameters into my new concatenated FCS file. Yes. Okay, and that I have done this already, this step, and we can go and see what we generate here. So we have a new sample, as you see here, which is called demo merge. And this is my concatenated sample from all the different macaques and the different time points. Yeah. So I will double click now here. And something we can see is the sample ID that I mentioned earlier. So we can see all of our different samples. And the order of the samples in the sample ID is basically going from top to bottom. So the left sample here will be the first one on my list, and second, etc. Something additional is that since we used keywords and we use those keywords for the concatenated file, we can use those into our axis. So now, for example, I can use day post-infection, and you can see at 0 now here, we have our, I will switch here to histogram. Yeah, so we can see at 0, we have the day 0 peak. Then we have at 7,000, we have the day 7, and at 28, we have the 28th day. Yeah, so, and this is an advantage of using numerical keywords, that as soon as you use those keywords in your concatenated file, those can be seen then on the right spot on your axis. Yeah. Okay, so, and now the next step would be to perform the dimensionality reduction. Yeah. So if I can adjust my microphone. Yes. Bad sound there.
It's okay now, thanks.
Ah, okay. Good. So now we're gonna go into dimensionality reduction. Yeah. So we can either use Disney, which is embedded already in FlowJo, and you can find it here. So it's no plugin. So as soon as you have FlowJo, you can have Disney and run it on your samples. Yeah. So by pressing Disney here, we would have to select all of our compensated parameters, apart from the ones that we already excluded, because they're not going to bring us any advantage into dimensionality reduction, since we already, for example, gated out our CD45. We can exclude the CD45 positive cells. And also we can exclude CD20 and CD3 that were excluded, and finally HLA-DR. Yeah. And there are, of course, some tunables here below that you can use, in case that you don't get a good separation of the islands, or if your Disney looks bad, you can always change the iteration, and you can change the perplexity and the algorithms that you will use for your testing. Yeah. I would suggest starting as it is, and if you observe weird structures on your Disney or anything that doesn't make sense, you can start thinking of adjusting those values. And in a similar way, you can use UMAP, TreeMap, PackMap, and the other dimensionality reduction methods. But in that case, those are, as Serena mentioned earlier, those are plugins that you can download for free in our FlowJo Exchange website. For example, you can find here UMAP, and again, same principle. We select our compensated parameters apart from the ones that we already used in our gating tree. Yeah. And of course, here in those cases, in UMAP and PackMap, we have some optional tunables, again, in order to adjust the number, for example, of nearest neighbors, or you can also adjust the trade-off between local and global structure. But once again, start by the defaults that are set according to the papers, and only if you meet trouble or if your embedded space doesn't look well, then you can think of adjusting those values. Okay, so let me go ahead and show you. I already ran those three dimensionality reduction methods, and I can show you how it looked like for this sample. So I will just go to my layout editor and go to dimensionality reduction methods. Okay, so here is how those algorithms looked, and this is the output we got from Disney, from UMAP, and for PackMap. Yeah, so you can see it might be that in UMAP, in PackMap, you already can see that we have more compact, so to say, clusters, and a very good separation in PackMap. Yeah, and in addition, since we have, we're talking about monocytes and differentiation of monocytes, you can see in both UMAP and PackMap those, so to say, trajectory lines that could indicate differentiation of one cell subset towards the other. And that's the advantage of having a global structure preservation compared to Disney, that you wouldn't be able to visualize something like this. And let's have a look now how, for example, those monocytes compare from method to method. So we can actually go to and overlay here our monocytes, yeah, and see how they look in this space. And that's because you can visualize your population of interest on both dimensions, on all methods, and see how it explained better, yeah, and how it visualized better. So I can transfer all three kinds of monocytes here. So here I have classical, intermediate, and non-classical monocytes. So you see now they're all spread, you know, around this embedded space. So I will remove this layer. So here we have the classical monocytes, we have our intermediate, and our non-classical here. Yeah, so their distribution seems to be random, right? So we don't have any global preservation of the data here. So we can try the same now for UMAP and PackMap. So let's do the same. I overlay those. And here it really looks much better. Yeah. So we can see, sorry, I will show the legend here. here so that we know what is what. Yeah. So we can see classical monocytes in blue, yeah, and then we have the intermediate and the non-classical as purple, orange color, yeah. So, and this is exactly, you know, the monocyte waterfall that we can visualize much better in UMAP and PACMAC rather in TSNE, yeah. So for this data set specifically, I would use one of the two, to be honest, instead of TSNE, so that I can also visualize those trajectories. But of course, it depends on always on your data set and what makes better representation, and you can always try multiple, as I did here, and see which one fits better to your data. Okay, so now no matter which dimensionality reduction method you want to use next, you will go for clustering, yeah, because you see here I have traditional gates again. I don't have, I have more diversity for sure here. I have different clusters here and here. So we want to do this automatically and identify all those clusters, yeah. Here I'll just remove here the different layers. It's okay, I will use another method. Okay, to perform clustering, you select again your merge sample, like I did here, and go to plugins and select your clustering algorithm. So I will use here EXIFT, which is the fastest of all, or you could also use FlowJo, but I will use EXIFT since I don't know how many clusters exactly we have in this data set. I'll go to EXIFT. If you want more information about how exactly this algorithm works, you can find more, can find the citation here, EXIFT published by Nikolai Samusik, if you're interested more into learning how those this algorithm works. In that case, again, similar to the dimensionality reduction, we will use the compensated parameters, and we will exclude the parameters that we already gated in or out. Yeah. So I do not want to have my HLADR since I gated an HLADR. I will exclude also CD20, CD3, and also I will exclude CD45 and CD8. Yeah. And I will press OK. So exit, you see how fast it is. Okay, and I think exit is done. Yes. So now we can see under our merge sample all of the different 14 clusters that EXIFT found. Yeah, so you can see the statistics here, and you know, those are labeled cluster 1, 2, 3, etc. So the first way to visualize this, you can do it again manually in the layout editor. So I could, you know, bring those 14 clusters into the TSNE, bring those into UMAP, and I can also bring those into my PACMAC. Yeah, so that's one way of visualizing those clusters, but still you don't get enough information in the sense of you don't know what each cluster of those expresses. Yeah. And that will bring me to my final part, that we're going to use Cluster Explorer to see what each one of those clusters corresponds to. So, so to use Cluster Explorer, it's again a plugin. So we will go to the plugin drop-down menu. And under plugins, we're going to select Cluster Explorer. So what the Cluster Explorer is going to do is to combine your clustering algorithm. So we will use our EXIF. Yeah, so we will use our EXIF. We will select our parameters of interest. So we'll again exclude the ones that I do not want to visualize and CDA. And finally, I can select my dimensionality reduction method. So you can use multiple. So I can have both Disney, UMAP, and PacMac and see interactively all of them and the cluster within those maps. Yeah. Select now, OK. And it's very fast, and it will generate all those plots here. Yeah. So what do we see here? I'll just order a bit the plots here, because there are many plots around. So we see here our Disney, our UMAP, put the Disney here, UMAP, and PacMac. Yeah, I'll use the PacMac here. So on the very first plot here, you can see the number of events per cluster. So we have 13 clusters, and you can select each one of those. So it's all interactive. I can select a specific cluster and visualize specifically the signature expression of these clusters. So now I know those are monocytes, they're CD14 positive, and I can see that also in the form of a heat map. So I see here those are CD14 high, and the nice thing is that you can compare how they look and where they're located in the different dimensionality reduction methods. So you can see here in PacMac, they're located here, Disney here, and UMAP here. Yeah. And I can then also select multiple clusters if I like. You know, I can select also cluster 11 and cluster 13. And in that case, again, all the plots will refresh. I will see where they're located in the dimensionality reduction methods and their expression level. So now we can see those monocytes. Those are classical monocytes, and they have different levels of expression of CD169. And that's why they're separate clusters and separate islands into these embedded spaces. Yeah. In addition, what you can do in Cluster Explorer is that you can also gate on those lines here. So I can, for example, form a gate here on my CD14 positive, and now I'm visualizing only my CD14 high cells in all the corresponding plots here. Yeah. Okay. And of course, you can also have an AND gate. So you can, for example, if you want to find the intermediate monocytes, you can form another gate here. So now we have double positive CD14 and CD16. Yeah, so those can be visualized, in UMAP here and in Disney all around. Yeah. Okay, I will clear now those gates and show you another thing in Cluster Explorer. You can change the global node here. So now we're visualizing all of our data. Yeah, so we visualize all of the different samples that we merged together, but you can change that and focus on a specific gate that you have under this sample. So I can select, for example, day 0. So now I have selected day 0, and I see only the clusters of day 0 in the different dimensionality reduced spaces and also their frequencies. So we see that during day 0, the main population is, the main cluster is cluster number 12, that, as we said before, cluster number 12 are CD14 positive monocytes, and they have, this is steady state, so we have CD169 negative. Yeah. So I can go now further, and I can see differences in day 7, for example. So this is how it looks at day 0, and this is how it looks at day 7. Yeah, so now we have inflammation. We have other clusters appearing. So for example, we have cluster 8 and cluster 13. Yeah. So as we see here, those are the cluster 8 is intermediate monocytes. So this is the presence of inflammation. We have double positive 14, 16. And we also have high 169 of our classical monocytes. Yeah, so now we can see at day 7, indeed, we can observe unique clusters, during ongoing infection. And finally, we can check at day 28. Yeah, so we have here again different clusters. So now we have different kind of classical monocytes with reduced 169, and we don't have any presence of intermediate monocytes anymore. So we have resolution of inflammation, and this can be seen here. Yeah, that's all what you can do with Cluster Explorer, and even more, it's a very powerful tool. If you want to visualize now all this, yeah. So sorry, I haven't mentioned, can also, if you want, visualize your traditional gates here. So classical monocytes, intermediate, yeah, and non-classical monocytes. So any gate that you draw on this sample, you can visualize it also here. Yeah. And one last thing I want to show you in Cluster Explorer. So let's say now we want to identify unique populations or unique clusters in one of those treatments or time points. You can also input that into the heat map here. Yeah. So as I showed you also in the presentation, you can add new nodes here. Yeah. So I can press this plus button, select nodes, and then I can add nodes as columns. Yeah. And now I need to select which columns I want to add. And that could be either the macaque IDs or the time points or whichever other gate I have already formed. So in that case, I will use my different time points and I will add those as columns. Yeah. So now you see as a heat map, so going from blue to yellow, we can see the abundance of each one of those clusters among the different time points. So when we see yellow, for example, here, so this cluster is abundant at 89% in day 0, so the uninfected, and also this cluster, which are the CD169 negative monocytes, are in day 0. And if you're searching for unique populations after treatments, so we can see those, for example, which are again proving the same, that the inflammatory, the intermediate monocytes appear at day 7, and that's why they're unique clusters at day 7, and they disappear after resolution at day 28. Yeah, so you can really use Cluster Explorer to really make your data ready for that interpretation and reach a point that you can have like explore really deep your data and know about which clusters appear, and use other tools in order to either isolate or sort those clusters and perform more experiments on this. And speaking of this, maybe a last plugin that I will show you here. So let's say now that we have interest on finding a gating strategy for this cluster. So for cluster number 8 that is present in after inflammation, we can use Hyperfinder in order to find an optimal gating strategy. Okay, because we're again in high dimensional data, and we want to find a way to sort this subset, and we can use for this the Hyperfinder plugin. So in Hyperfinder, we can select the parameters that we want and the cluster. Okay, so we can select cluster 8, and then cluster Hyperfinder will find an optimal gating strategy for this tool. I have a different build that I was testing, so I would rather not proceed with the Hyperfinder. But in theory, then in the end, you would have gates that were identified with machine learning and were adjusted in order to get the highest yield and purity in order to sort this cluster. And after you have those gates, you can always select them, and then you can export those gates into FACSDiva. Yeah, and then you can go to FACSDiva, perform the same experiment, and then sort out this specific cluster for single cell RNA-seq or any downstream application you wish to proceed with. Okay, so I think this is the last part I wanted to show you. Sorry for all the delays that happened with my laptop this morning. So for any other question that you might have, we're really here for you. We have both our email addresses here. I want to thank Serena for joining here and answering all those questions in the meantime. And for anything you have, please contact us, and we're really happy to help you with your analysis. So thank you all very much.
Thank you, guys.